Hello, my name is Ali Aminasiri and the topic of my project is non-unique flow solutions in double-sided lid-driven cavity. The Navier-Stokes equations are nonlinear and thus have the potential of producing multiple flow solutions. Prumal used the Lattice-Boltzmann method with a single relaxation time to obtain multiple steady flow solutions for the double-sided lid-driven cavity problem with varying Reynolds number and cavity aspect ratios. The goal of this project is to reproduce the multiple steady flow solutions obtained by Prumal but using the Lattice-Boltzmann method with two relaxation times instead. The two relaxation time model of the Lattice-Boltzmann method is favorable as it offers better stability than the single relaxation time model, especially for flows with high Reynolds numbers. Here I provide some clarifications about the numerical method. For the Lattice-Boltzmann method with two relaxation time, the distribution function and equilibrium distribution function are split into symmetric and antisymmetric parts. The superscript S denotes the symmetric part and the superscript A denotes the antisymmetric part. F minus I is the distribution function with lattice velocities opposite to the ones of Fi. The post-collision distribution function, which is Fi star after the collision or relaxation step, is written as the first equation in this slide, with the lattice time step size delta t being 1 and the relaxation frequency is defined as the following. The post-collision distribution function can be rewritten as the equation in the green box. The new distribution function after the propagation or streaming step is written as the first equation in this slide. Considering delta t equals to 1, it can be written as the equation in the green box. The symmetrical relaxation time can be chosen based on the relationship for viscosity, the top left relationship, where the kinematic viscosity is dependent on the Reynolds number, lead velocity, and mesh size. The antisymmetric relaxation time can be chosen based on the magic parameter. The magic parameter was chosen to be a quarter to obtain the best stability for the algorithm. The bounce-back method was used to impose boundary conditions on the velocity at the stationary and moving cavity walls. The method was implemented by placing the solid boundary in between two lattice nodes n and n+1 as shown in the figure. No boundary conditions were imposed on the pressure. Here I would like to explain the results of the project. The first case considered was a double-sided rectangular cavity with an aspect ratio of 1 with parallel wall movement. The top and bottom boundaries move with a constant velocity of u in the same direction. The critical Reynolds number where non-unique steady solutions occur for case 1 was found at Reynolds numbers of 985.5. For this case, 4 different Reynolds numbers of 500, 1000, 2000, and 3000 were considered. Based on the streamlines shown in these figures, symmetrical solutions were found for all 4 Reynolds numbers, where the flow is symmetrical about the y-axis. At Reynolds numbers of 500, small secondary vortices began to develop near the right cavity wall. They are also symmetrical about the y-axis and increase in size with Reynolds number. Based on this table, the center of the upper primary vortex moves towards the x-center line with the increase in Reynolds number. The results obtained with the present Lattice-Boltzmann method with two relaxation times are consistent with the results obtained by Lemmy and others using a finite difference scheme and by Prumal using the Lattice-Boltzmann method with one relaxation time. Asymmetrical solutions were found for Reynolds numbers of 1500, 2000, and 3000 as shown in this figure. As the Reynolds number increases, the secondary vortex in the top left corner in this figure increases in size, while secondary vortex on the top right corner decreases in size. The locations of the primary and secondary vortices are shown in this table and are also consistent with the results obtained by Lemmy and Prumal. The second case considered was a double-sided rectangular cavity with an aspect ratio of 0.875 and parallel wall movements. The left and right boundaries move with a constant velocity of u downwards. The critical Reynolds numbers where multiple steady solutions occur for case 2 was found at Reynolds numbers of 600. For this case, 4 different Reynolds numbers of 50, 200, 500, and 600 were considered. For all 4 Reynolds numbers, symmetrical solutions were found as shown in this figure, with the streamlines being symmetrical along the vertical center lines. The primary vortex sensors migrated towards the horizontal center line with the increase of Reynolds number. The symmetrical solutions found are in good agreement with the ones obtained by Prumal. Prumal found 5 non-unique solutions for this case, with 1 being symmetrical and 4 being asymmetrical. The four asymmetrical solutions are two pairs of solutions that have mirrored flow patterns. However, no other steady flow solutions were found besides the symmetrical ones shown in the previous figure with the present lattice Boltzmann method. The third case considered was a double-sided rectangular cavity with an aspect ratio of 2 and anti-parallel wall movements. The top and bottom boundaries move with a constant velocity of u in opposite directions. The critical Reynolds numbers where multiple steady solutions occur for case 3 was found at Reynolds numbers of 700. For this case, four different Reynolds numbers of 50, 200, 500, and 700 were considered. At Reynolds numbers of 50, two weakly merged vortices were generated with the vortex centers near the top right and bottom left corners of the cavity. At Reynolds numbers of 200, the two primary vortices are still merged, but they appear more circular and the vortex centers are closer to the vertical center line. In addition to the primary vortices, two secondary vortices near the horizontal center line were also generated. At the Reynolds numbers of 500, the primary vortices separate and the secondary vortices merge into one long vortex separating two primary vortices. At Reynolds numbers of 700, the flow pattern remains similar to the one at Reynolds numbers of 500. Prumol found 7 steady solutions at Reynolds numbers of 700. Of all the solutions identified by Prumol at Reynolds numbers of 700, only the ones shown in this figure were found with the present Lattice-Boltzmann method. Like the asymmetrical solutions found in case 1, the mirrored version of the solution in the part C of this figure is also a solution. Therefore, 4 steady solutions were discovered for case 3 at Reynolds numbers of 700 for this project. These are the conclusions of this project, which I already have mentioned. These are the references I used in this presentation. Unfortunately, I was unable to attend the presentation session. Please feel free to send any questions you may have via email. Thank you very much and have a wonderful day.